Hello, in this podcast we're going to learn how energy flows, and our learning objectives are to describe the different forms of energy, explain the first two laws of thermodynamics, and explain how energy flows in an ecosystem. First of all, we need to define what energy is. We learned earlier that matter is things. Everything that you see is made of matter, and matter is anything that has mass and volume. Energy is different. Energy is the ability to do things. So when things are done, it takes energy. The list you see here are some of the more common forms of energy. There is kinetic energy, which is the energy of motion, and potential energy, which is the energy of position. The two of them are frequently learned together because those two change into each other very quickly and very easily. For example, if you right now pick up a book, and what you've done is you've taken the chemical energy that's within the bonds of sugar in your muscle cells, and you've converted that to energy, and that energy went into the book when you raised it up. That's potential energy, energy of position. Now drop the book. That energy of position transferred into energy of motion, and that's kinetic energy. Then there is sound energy, like if your floor isn't carpeted, then the book probably made a sound as it hit the floor, and that sound is energy. Also, when you lifted up the book, some of that chemical energy converted into heat. It's not enough for you to really sense. If you do a lot of that type of energy, then you would. Like if you lift weights, then you start sweating because you produce so much more heat. Another name for heat energy is thermal energy. Another kind of energy is electromagnetic radiation. This is basically light energy. It can be visible light, which is a very small portion of electromagnetic energy, or invisible light. And here's the list of different types of electromagnetic radiation, different types of lights. This is going from most energetic to least energetic, going from gamma rays to X-rays to ultraviolet to visible to infrared to microwave and to radio. Now I'll go into the first law of thermodynamics. Now the first law of thermodynamics is the conservation of energy. Basically, it states that energy can neither be created nor destroyed. It can only change forms. Like what you see in the diagram over here is the rock is potential energy of 10 kilojoules. Joules and kilojoules are a unit of energy. Another one that you see a lot of is calories. And when that rock drops, then it speeds up, so potential energy is then transferred into kinetic energy. Now, if you add those two energies up, you see you got 7 plus 3, which is 10, which is what we started off with. The most famous equation in all of science, E equals mc squared, is the same thing. In a nuclear reaction, a tiny bit of matter is converted into energy, and it makes a lot of energy because c is the speed of light. So a little bit of matter times the speed of light times the speed of light gives you the amount of energy. Another example of the amount of matter and energy being conserved would be like in this match. This match, you've got matter in the form of ignition in this part of the match, which very easily lights up, and then you've got all the chemical energy in the wood. You've got the wood itself. Now, if I were to take this match and strike it, what's happening is that the chemical energy is turning into light energy and heat energy. And also the way it's doing that is that bonds are being broken in the wood in the match, and you see the amount of matter in the match is getting less and less, and the simple reason for that is because the bonds are being broken and it's making other forms. It's making carbon dioxide, it's making water, and the smoke you see is because some carbon is coming up, and that is from incomplete burning. If it was burning very cleanly, then you wouldn't see any smoke. It would just be carbon dioxide and water. Second law of thermodynamics, and that basically states that when energy changes forms, it always changes to a lower quality or a less useful form. Like what we saw in the match here is that the wood here was very useful. You could use it for things. But the less useful form was the heat that came out and is now dispersed throughout the room, and carbon dioxide, which we really can't use at all. This is called entropy. And entropy is the amount of disorder, and the second law of thermodynamics says that entropy always increases. The form is usually heat, but keep in mind that locally the entropy can increase. It's when you look at it globally that it decreases. For example, when a plant uses photosynthesis to take carbon dioxide and water and puts it together, their entropy is increasing because sugar is much more useful and has much more order than carbon dioxide and water. But if you look at it overall, the overall picture, the entropy will increase because where's the plant getting its energy from? It's getting it from the sun. So when you add together the entropy that is increasing in the sun, that is actually greater than the entropy that's decreasing in the plant. So overall entropy is increasing, and it's not breaks the second law of thermodynamics. And actually both the first and second law of thermodynamics are never ever broken. Another example of second law of thermodynamics would be a light bulb. If you look at the old incandescent light bulbs, like this one here, they give off a lot of heat. You don't want to touch them. They're hot enough to burn you. 95% of that energy that is coming through the wires gets lost to heat. It doesn't go out as light. That type of light bulb is one of the most inefficient things that we've ever invented. And that's why there's now a law that makes the sale of these actually illegal. If you go to a store, you cannot buy a 100-watt light bulb. Instead, you have to buy an energy-efficient light bulb, which uses a lot less energy. And that brings us to energy efficiency or energy productivity, which are the same things. And that's a measure of how much useful work is done when compared to how much energy is used. An equation for that is what we see over here, that work out divided by energy in times 100% is the energy efficiency. And how is energy lost? It's lost through the second law of thermodynamics. It's also lost through waste. We don't always use the most efficient ways of using energy. And light bulbs are an excellent example of that. Over here we have two light bulbs. We have the old style incandescent light bulbs, and we have the LED light bulbs. The third one I don't have there are the compact fluorescent light bulbs, or CFCs. A 100-watt incandescent bulb produces the same amount of light as a 19-watt LED bulb. Incandescent light bulbs waste much more energy in use. Like if you ever feel LED bulb, it's not going to get anywhere near as hot as a 100-watt light bulb. There's another form of waste that you don't immediately see, or you wouldn't see unless you actually look for it. And that is that the incandescent light bulbs last for only about a year. The LED light bulbs can last for 15 to 25 years, or even more. This means that the energy lost is not just in terms of light in light bulb. The energy is also lost because a lot more incandescent light bulbs, 15 to 25 more bulbs, need to be produced and disposed of. And that's quite a bit of energy. Energy in terms of making the glass, mining the filaments and other metals that are composed in light bulb. All of this takes up a lot of energy and also a lot of waste too. See these things as we go on through the year. Environmental implications of these laws. There are basically two sources of energy here on this planet. There's the sun and the radioactivity of radioactive elements in the inside of the earth. All other energy comes from these two. An example of that is that the fossil fuels, oil, natural gas, coal, all of those, they're called fossil fuels because they are fossils. They come from fossilized plants which died millions of years ago, in some cases hundreds of millions of years ago, and they received that energy from that energy, all that energy in there came from the sun. As this energy is transformed, less is available for use. Some implications of that is that more energy is available for plants and for predators. And that's why, if you look out your window, you'll see lots and lots of plants, but you will not see a lot of predators. When society uses fewer energy transformations, expenses will be less and the environmental impact will be less. Example of this is that if your clothes dryer is a gas-powered clothes dryer, then all the heat that it gets is produced by burning natural gas in the dryer. So that's one transformation. This uses less energy than an electric-powered clothes dryer, which still burns fossil fuels like natural gas in a power plant. That same percentage that's lost in a clothes dryer is most likely also lost in a power plant. But it's happening miles away from your home. That heat energy that is produced by the burning is transformed to electricity, And the way that's done is by turning a magnet in an electrical coil, and we'll see this later in the year. And that energy is then lost in the wires on the way to your home. One way you can sort of see this is how it's lost is if you ever used a hair dryer and kept it going for a while, you may notice that the wire there gets a bit warm. That always happens whenever electricity is going through a wire. You don't always notice it because it's very little, but still it's there. The longer the wire is, the more it gets lost. That electricity then gets converted into heat in the dryer, and that then dries your clothes. There's several transformations along there. More energy gets lost that way. Now I'll tell you, when you go to buy a dryer, a gas-powered clothes dryer does cost about $100 more than an electric clothes dryer. However, over time, your savings will be much greater using a gas-powered clothes dryer than using an electric-powered clothes dryer. And the energy loss is one of the reasons why. Now we come to our concluding questions. Number 1, define energy and describe 2 examples. Number 2, define the 2 laws of thermodynamics and give an example of each. Number 3, a car has 15% energy efficiency. What does this mean? That concludes this podcast, and I'll see you in class tomorrow.